find the derivative of x to the x. Well, I think these facts are good if you would like to use an implicit differentiation approach to this problem, which is my favorite, my personal favorite. There are, of course, other ways to do this problem, and that's, again, the beauty of mathematics. So, how would you do this problem implicitly? Well, you would start by letting your weird, obscure function x to the x be equal to y for some y. So let's say it's equal to some value. Then in that case, the derivative with respect to x of x to the x is going to be the derivative of y with respect to x. Or I could say the rate of change of y with respect to x. So maybe in more steps I would write d by dx of y, and so the derivative of y is 1, but I need to consider dy by dx because the rate of change of y with respect to the rate of change of x is not the same. So if dx by dx is fine, x changes as fast as x, but with y and x we don't know. There is a certain relation between them which we still need to unravel. So that is a good use of what is called the chain rule. So we proceed, and you probably see already there's an ln of x here. So probably we need to introduce the ln of x. And it is quite useful indeed to introduce it when you have a setup like this one, where you have an exponent, which is a variable. So your exponent is not a constant, it's a variable, which is x. So that is somewhat problematic. We don't know how the function would behave. So in this case, what we would do is we can use the property of the logarithm, which I forgot to write down. And that is, if you have ln of, let's say, some base to some exponent n, then you can write it as n times ln of b. So in other words, the exponent can become a coefficient of the ln function. And precisely this is what we do in the next step. So we get x ln of, let's write in one color, is equal to ln of y. And now this is a bit nicer. We can start working with that. Precisely, we would start taking the derivative in the next step. And so, we take the derivative with respect to x on the left-hand side. We have a product of two functions. So we would use the product rule, which tells us that we only need to fix one term, take the derivative of the other, and then add, and then do the opposite and sum up the values. So we would do the same. We would take the derivative of x and fix ln of x. This is just the left-hand side. On the right-hand side, we have the derivative of ln of y, which is 1 over y by the first point. Almost, because you still need to use the chain rule. Because y is a function of x. Yes, it is. So it is a function of x. So you need to consider dy by dx. Because as I said, the rate of change is not clear. It's not a given value. But here's this. What's dy by dx? It's our intended outcome. So we're looking for d by dx of x to the x, but it suffices to find dy by dx, because they're literally the same thing. If this is true, then that is true. So we just need to find this. Or in other words, we need to solve for this. First, let me take the derivative on the left-hand side. So you have x times the derivative of ln of x, which is 1 over x. So clearly they cancel out. And then we add the derivative of x, which is 1. If you have a line, the graph of the line y is equal to x has slope 1. Fundamentally, the derivative is also the slope on very small intervals. So this is 1, and you have ln of x. 1 times ln of x is fine. You can just write ln of x. Now this is equal to 1 over y times dy by dx. So I hope you don't mind if I multiply both sides by 1 over y. I don't think there's going to be a problem with that. I hope. I hope so. I could be wrong, of course, as with many things. So this is 1. That is ln of x. And we multiply this by 1 over y. Maybe I'll give it another color, which is light blue. Then this light blue y would be this. But then y is x to the x. So I'll just write x to the x. And on the right hand side, I'll get dy by dx. So that looks a lot like the solution, because dy by dx is just the derivative with respect to x of x to the x. Maybe it would be nicer if I do it in brown, because brown is a nice color. And then it just remains to put this in a nice box and we are done. And for this kind of problem, you just need to know these facts. As a general rule, almost all implicit differentiation cases are concerned with stuff being stuck in exponents. So this can get more complicated. For example, I might ask you to find x to the x to the x, the derivative of that. So that would be a very good exercise. Or you could do x to the, let's say, even e to the x, because I'm a weird person and I want you to compute it. So in general, I don't think you'll get derivatives of this sort, but it is good practice to at least know how to navigate your way through stuff like this. And it is also good practice to be able to break your problem down into smaller pieces, as we've done here. So first with the product rule, before that with the introduction of y, and then with the manipulation with the exponent, and then we have a very nice structure which can be applied to other problems of the same sort. This is it.